Hi, and welcome to our introduction to member design training. My name is Clemens Goodman, and I am responsible for customer support and product engineering, especially the topics of form finding and Win simulation. And I'll present to you the first part of this training together with my colleague, Niklas Wanke, who can introduce himself.
Yes, good day, everyone. Thank you, Clemens, for the introductory words. I would also like to introduce myself briefly. My name is Niklas Wanke, and I'm responsible at Dlubal for the customer support as well as for product development in the steel construction sector. And today I will present the second part of the student training for you. But now, Clemens, it's your turn and you can get started.
Thanks. So let's turn off the camera so everybody can see the full screen, and we'll jump right into it. At first, one technical thing, you can ask questions during the presentation by clicking on the icon with a question mark on the top right corner or in the top right corner, and enter the question into the box and hit send. During the first part of the presentation, my colleague Niklas Wanke will try to answer your question, and after the break in the roundabout the middle of the presentation, we'll switch places and I'll answer your questions while he's presenting. If we are unable to answer any of your questions due to the time or due to the complexity, we answer afterwards via email to your question. So feel free to ask as many questions as you like. We are happy to answer them. Regarding the content, I give a brief introduction to the Rfem user interface in the beginning. After that, we'll jump right into the program and try to model and analyze a single span beam as an introductory example. After that, we have prepared several advanced analysis examples, of which I'll present 3 to you. And after those 3, we'll have a short coffee break of 10 minutes. After the coffee break, my colleague Niklas will continue with the presentation and present to you another 3 examples before he'll get to the chapter with the influence of the second order theory, where we'll show you what effects the use of the second order theory calculation has. And last but not least, we have the topic of the stability analysis, where we show you how to perform such a stability analysis and what effects there are for you to explore. So the user interface of Rfem 6 as well as comparable software is at first glance a little bit complex, like an airplane, lots of buttons and setting options. And to ease the entry into the program, we broke down this user interface into several parts, and I'll briefly describe the single parts. So in the top left, we have a menu bar, like in other programs as well. On the top right, we have a search box where you can search for options and functions and so on. So if ever you forgot where to change something or where to create something, where to find a button, just go into the search box and search for it. Below, we have a toolbar with different icons to create elements, to start the calculation, to manipulate the view, to save the model, and so on. In the center, we have the workspace, 3D workspace, which can be manipulated via mouse, and a view cube in the top right corner. On the left-hand side, we have the navigator, like a tree structure you might know from the Windows Explorer. And in that tree, all elements and objects you create are sorted in, like listed. We'll see that later on because we'll work a lot in that navigator. All the elements that you have in the navigator are in a different kind of view, also available at the bottom in the table. So yeah, it's just a different approach. In the table, you can see more specific settings of the single objects directly in a table view. We have an AI assistant called Mia. She is trained to answer technical questions, generally about civil engineering, but especially, of course, for the program. So if you have any questions, regarding more complex elements, then just using the search box, just ask her. You don't have to leave the program. She'll dock in a sidebar on the right-hand side. And last but not least, at the very bottom, we have another toolbar that contains the different commands, especially regarding drawing, so manipulating geometry, snap points, working grid, and all of this stuff. So that's it for the user interface, and I'll say we jump into the software and have a deeper look how to model something and analyze something. And the first thing that we want to analyze is a single span beam with a concentrated load. And for that, we first model this beam, then apply a concentrated load to that beam. We'll calculate the model and inspect the results, especially the support reactions, the internal forces, and the deformation. So let's jump right into the software. And if you open the software for the first time, it's a little bit gray, but that'll change very quickly once we created a new model. And that we can do in 3 different ways. One way is to right-click on the Rfem icon in the data navigator. Second way is to go into the menu bar, File, New, and the third possibility is the icon in the toolbar. I'll click on that, and a new dialog opens and asks for a model name. I'll type in single span beam because that's what we want to analyze. Then we can select a model type. Since we want to analyze a 2D structure, I select the second option, 2D plane stress. That simplifies some parts. And then we have different tabs. I want to mention one tab, the add-on tab. So Rfem by default provides a basic set of modeling and analyzing, and there are a lot of additional add-ons for the program available. And if you check one or multiple of these add-ons, the program is extended by functions, entries, and so on, everything you need for that add-on. So everything integrates into the software. There's no additional new window or something. It's everything. There are new entries in the data navigator, in the table, and so on. But there are specific trainings for these design add-ons, especially design add-ons. And if you are interested in what these, make sure to subscribe and look into them. My colleagues will show you everything to know. For now, we apply by clicking on OK. And now everything brightens up and gets more colorful. We now see the image live that I showed you in the presentation before. So we have the main workspace in the middle, and it's a 3D workspace, as I told you before. And to navigate this workspace, there are different possibilities. One is your mouse. So if you click the mouse wheel and hold it, you can pan. If you simultaneously press and hold the Control key, you can rotate. And the other possibility is to drag the view cube over here, or to click on one of its faces, edges, or corners in the way you need it. And as I said, the program and similar software as well can be quite overwhelming when using it the first time or even first times. And to give you a little hint how to make life easier for you, go into the data navigator and work yourself from top to bottom. Then you have the correct, or like a red thread, a red string where you can hold on to. So that's what we're going to do. And the first entry here is materials. And that's why we're going to create a material at first. So you right click on material and go to new material. And then another dialog opens where we can enter the properties of that material, but you don't have to enter them by yourself. We have a very comprehensive library available through the book icon. And there are lots of materials for lots of standards and lots of regions available, a very, very long list. And you can filter through that list using these filter options on the left-hand side. And I want to do that. I go on European Union, steel, carbon steel, and as a standard, I use the Eurocode 3, chapter 1.1. And then the list is very, very short. And I select the S235. I click OK. And the material properties from the library are being transferred into the material. The material type changed from basic to steel. And we can inspect all the material values over this tab. And if I click OK, this material is being created. We can see that in the data navigator, there's a new entry here. And additionally, we can see this also in the table. There's a new line with the materials properties where we can inspect them directly, and we do not have to go back into the dialog. Next step, create a section. I could use the context menu again, but I want to show you a different way. I go into Insert, Basic Objects, Sections, Dialog. And for sections, we also have a big library available through the book icon. And there is not like one big library. You have a pre-selection at first. So you have standard-sized, built-up, thin-walled, massive sections and parametric bar sections. And I want to use a standardized I-beam for my project. And then inside of that category, we have now the list of available sections. And this time I do not want to use the filter, but another option, and that is a search box. And I search for HEA 200. And I want to use a European section of the HEA. I click OK. And again, all the section properties have been transferred to the section dialog. And as you can see, also here, there are lots of different tabs with different information. And I recommend to you that you explore the software with some curiosity and try things out. I think this is the best and quickest way to get to know the software, to feel comfortable using it. So just go ahead and click on tabs and icons and options, and explore the software by yourself. I can only show you some basic elements, but there are, as I said, so many possibilities, and you can learn a lot by just exploring the software and its features. We click OK, and the section is now available. So you might have noticed that the material was before displayed in a blue color, like the section is now, and now it's displayed in a black color. And that is because objects that are not in use by any other object are being displayed in a blue color. And by the time we only had a material, the material was not used by anything else. So it was displayed with a blue color. And now the material is used by the section we just created. And that is the reason why it's now black. And since the section is not used by any member, the section is temporarily displayed in a blue color. But once we created a member, it will be in a black color. So just so you know, if you have any blue entries, that means that these entries are not in use in the model. Good. Now let's define some geometry. I showed you the possibility to create objects in the data navigator and via the menu bar, but there's a third option, and this is the toolbar. I click on that icon for new node, and a small dialog opens up, and now we are able to graphically decide where to put a node. And you might notice that if you move the cursor around, it snaps to the small dots, and this is our working grid with a dimension of 1 by 1 meter. And this helps to place correctly our node. And I want to create a node in the origin, so X and Z0. I click on it, and the node has been created. And we cannot see it right now because the coordinate system is blocking the visibility of the node, but we can see that it has been created because it's available in the data navigator. And we can get rid of the coordinate system by clicking on the display tab in the navigator. So there's a display tab where you can adjust all different available settings regarding the display of objects in the workspace. And the option we search for is the global coordinate system in the origin. And if I uncheck this, the coordinate system disappears and the node is visible. Okay, now we could use the same workflow again to create a second node, and our beam is supposed to have a length of 7.5 meters. And now we have a little issue. So our grid only allows us 7 and 8 meters, but there's no snap point for 7.5 meters. So there are two possibilities to solve this. One possibility would be to adjust the grid. So I could go here to Tools and then Work Plane and adjust the spacing of the grid to 0.5 meters in each direction and hit OK. And that way, a snap point would be available at 7.5 meters. But I do not want to do that. I want to show you a different possibility, fourth possibility to create objects. So we had the data navigator, we had the menu bar, and we had the toolbar. And the fourth and last option is the table. The table has two drop-down menus, and then depending on what entry you select in the drop-down menu, different tabs. And the node tab is under Structure Basic Object. And we can see our first node that we have created graphically already. And if we click into the second row, we then can enter the coordinates of our second node using our keyboard. And as I said, the beam is supposed to have a length of 7.5 meters and a Z coordinate of 0. And you can already see that there's a faint display of that node in the workspace already visible. And if we click in another row, the node is created and now displayed in a bright red color as the other one. Next step is to define a line between those two nodes. I choose the way over the data navigator, new line, polyline. And the dialog then asks us for the node numbers that shall be connected by that line. And I click on the pick icon here, and then I can graphically pick those two nodes, the line, click OK, and OK again, and the line is created. The next entry in the data navigator now is members, and I want to create a new member. And a member is basically a property of the line. So to create a member, it is necessary to have a line that the member is attached to, so to say. And I want to show you another way of interacting with the software is if you double click on any element in the workspace or in the data navigator, the according dialog with the properties of that element opens up. So if a member is a property of a line, I can double click on that line and I can assign this property to that line by clicking on member. And now the member dialog opens up, and I can define that member. And there are not that many options by default. So the most important one is the member type. And yeah, by default, the member type beam is selected. And you can see on the right a graphic where you can see which internal forces this member type supports. So if you select a different, for example, truss, you can see that some of the internal forces are removed. And so that means that this member type can only bear these reduced set of member internal forces. And yeah, as you can see, there are a lot of different options. And if you at this point or any other point don't know what different options or properties and settings mean, there's always a good possibility to learn something by clicking on the help icon down below. It can be found in almost every dialog in the bottom left corner, and it leads to our website and into our online manual. And it jumps right into the according section where you are right now. So we have been in the member section, and now we see the page where everything is described for the member type, for example. So here you can read everything about the different member types, what they do, what properties they have. So if you ever want to learn something about the what different options and settings do, just click on the help icon and read the online manual. Good. I want to create a member of type beam, so the default settings are okay. And in the section tab, we can select a section. And since we only have one section, it's already been selected, so that's okay. We click OK, and again OK. And now that member is created along that line, and there's also a rendering of that member now visible. At some point, you might get rid of this rendering, and there's an icon in the toolbox that does that, and it's the one here. You can choose between 3 different types of model displaying. There's the wireframe option, where you can only see the lines and no section. There's a solid rendering, where you can not see through objects. And there's a transparent option, where you can see objects that lay behind an object. Okay, I'll switch to our normal view again. And for now we are done with the basic objects, and we move further down to the types of nodes. So in Rfem 6, you have the basic objects, and then you have so-called types for basic object. And what we want to define now is a nodal support. And since a nodal support is a property of a node, it is a type for a node. So this is the main concept behind this. And there are some predefined nodal supports, and since they are not in use, they are displayed in a blue color, as I said before. and I want to assign that nodal support to the left node, the hinged one, and there's an object in the context menu that says assign to nodes graphically. And if I click that, I can pick the node, hit OK, and this type for nodal support is assigned to that node. I repeat this for the right node with a roller nodal support. Again, and now the support is defined. If we double click on this entry in the data navigator, the corresponding dialog opens up and we can inspect the different properties for that nodal support and make changes if we want to. But for now, the settings are fine, so I'll just close it by clicking OK. Good. Next step, we skip some parts, are load cases, but we already have predefined a load case, so we only need one, so there's nothing to do here. And the next relevant entry is loads. And we are supposed to apply a concentrated force at 4.5 meters from the left side onto the beam. And we do not have a node right now at that spot. So what are we going to do to create a node there? We right-click on the member and go to Members, and then divide member by distance. And then we can specify a distance from the member start, which is on the left side, because there's this black arrow pointing to the right, to the beam's end, to the member's end. And so if we enter 4.5 meters, everything else is being adjusted automatically. And there's another option I want to show you. So there's this option, create on member nodes without dividing a member. So if I would click OK right now, the member would be divided into two members. But as we have seen before, there are different node types, and there's another node type that comes in sometimes quite handy, and that is the node type on member. And if I click OK, you can see that there's a blue displayed node now available, and that the beam is not divided. This has some advantages later on if you, for example, have to design this member. So yeah, just so you know that there are different node types, and I think this node type on member comes in quite handy at sometimes. Okay, and now we can define the nodal load. I click on the icon for new nodal load in the toolbar, and now I am asked to which node I want to apply this load to, and I pick the newly created node. And now I have to specify the force. The force is 10 kilonewtons. I click OK, and the force is created. Good. Now we have reached the end of the list in the data navigator, and the next entry is results. And in order to get these, we have to calculate the model. And I do this by going into the menu and click on Calculate Current Loading. Now the model is transferred to the solver, and the solver calculates a solution for this model and it loads. And now we can see that the data navigator disappeared and a new result navigator is being displayed. But the data navigator is not gone, it's just a different tab here in the navigator. Good. So if you check out the different options in the data navigator, you can see that we can inspect deformations, you can inspect different member results, for example, the internal forces, and we can inspect support reactions. And one thing you always want to do is to run a quick plausibility check when calculating models. And I want to check whether the load that we put into the structure also sums up in the support reactions. And we applied a load of 10 kilonewtons, and apparently we get more than 10 kilonewtons as a result. And why is that? We can check one thing. So in the results tables, we can see that the sum of loads in the Z direction are 13.17, and also the sum of support forces are 13.17, and the deviation is 0%. So there must be some load applied to the model that we cannot see. And the reason for that is that in the load case that has been by default there, self-weight, if we look into this, we can see that there's an option activated for the active self-weight. And this self-weight is not displayed currently, but we can make this visible using a coding option in the display navigator, here self-weight. And now we can see that there's a constant load applied to that member, and that leads to the higher support reactions. So if we go back into the load case and deactivate the self-weight for now and recalculate this load case, we can then see that the 10 kilonewtons of load is exactly the 10 kilonewtons of support reactions. So this is good. So I recommend you to always run a quick plausibility check if you are modeling and analyzing, because it happens quite often that you make some mistakes, that you oversee something, and to not drag around some mistakes, it's always I recommend you to run a quick plausibility check, and the sum of forces, for example, in the Z direction is a good start for doing that. And now we want to inspect some of the results. So we have the global deformation, and it delivers a plausible result. We have then the bending moment with 18 kilonewtons. This is also plausible, and we can see if the corresponding VZ force is also good. This corresponds with the support reactions and also with the applied loads. So we get a good result, and yeah, we fulfilled all tasks for that. Yeah, that were given to us with a single span beam. So let's go back and pick the next example for our next model. And the next example we want to model and analyze together is the two-span beam with altering load position. And this model consists of an HEB 300 with an S235 material, as well as 3 different load cases, a self-weight load case and 2 imposed load cases. And we are asked to determine the forces of the support, internal forces, and deformations. Additionally, we are asked to determine the governing load combinations that cause the largest internal forces. So let's jump back in and let us create a new model for that. So two-span beam. And again, I want to use the model type 2D plane stress like before and click OK. Now we have again a blank canvas, and we just do the same routine as we did before, starting by creating a new material. And if you know what material you want to use and how it is called or spelled, you don't have to go into the library, but you can search for it in the name box. So if I search for S235, it gives me all entries of the material library that match this description. And if I scroll down, I can find the S235 of the Eurocode 3 almost at the bottom. And if I click on it, it is selected. And now I have to hit the Tab key on the keyboard. And now the data is transferred into the dialog. I can click OK, and the material is created. I repeat this for the section. So by default, there's a specific section, but I can delete this entry and again search for an HEB 300. And I want to use again this Euronorm entry. Click again or hit again the Tab key on the keyboard, and the entries are copied. We click OK. And now we want to model our structure. And before we created the nodes, then the line between the nodes, and then the member on the line. You do not have to do it that way. I just wanted to show you how everything is built up from the ground. There's a quicker way that I want to show you to do exact this. Yeah, and that is by creating the member directly. And if you go into the toolbar, you can click down here on that arrow, and it gives you a different options for creating members. So you can create a single member in a simple manner, a single member in a general member where you have more options, and you have the possibility to create multiple members that are connected in a continuous way. And I want to do this in a simple way. So now I am asked to define the properties of that member. I again want to use the member type beam, so that's okay. And then I can graphically draw that member. So I start at the origin, click once, and we have a field length of 2 times 5 meters. So I search the grid point at 5 meters and then again 10 meters. Then I click cancel because I created everything I need. And what happened now is that not only the member has been created, or 2 members have been created, but simultaneously the 2 lines for the members have been created and the 3 nodes have been created automatically by the software. Because as I said, you always need the lines and the nodes, but you do not have to define them beforehand. You can create them all together in one step. Now we want to support our model again with a hinged support, and I want to assign those nodes graphically here for the hinged. And for the roller, I want to show you a different approach. So if you go back into the table and in the right drop-down, you find types for nodes. And here you can find the node number 1 that has been assigned to the nodal support number 1. And I want to assign the nodal support number 3 to the 2 other nodes, 2 and 3. And I can do this by clicking into this cell and just typing 2, 3, and then deselect that cell by clicking somewhere else. And as you can see, a little bit small, the supports have been assigned to that node. And you can scale these member supports by right-clicking on one of them and adjusting that slider to a size that you like. I make it a little bit bigger so you can see it well. Now we can go on and define our load cases. And there's a button also in the toolbar for the load cases. That is this one, Edit Active Load Case. And it brings you to the dialog here where you can define the load cases and all the combinations. So the first tab is the base tab, where you can select the standard and the national annex according to which the combination is to be performed. And you have another option called Combination Wizard, and this is a function that does the combination for you according the selected standard. And we'll see this in a few seconds. Okay, so I go back to the load cases tab, and by default there's already a self-weight tab, a self-weight load case, and I want to create a new load case, and I give this load case a name, imposed load left, and I choose a different action category because this imposed load is not a permanent load but an imposed load. I'll just select category A for now, and then I can reuse these settings that I made of this load case by duplicating this load case and just changing the name to right. Good. And the next tab is the Actions tab, and there the single load cases are grouped into the action groups. So we have the self-weight being assigned to the permanent action and the 2 imposed load cases assigned to the imposed load action category. And you can see that there's another option here with the action type, where you can select how the single load cases in one of the groups is being combined later on. So simultaneously means that, okay, this is like action category 1 is not interesting because it only has 1 load case, but action category 2, you have 2 load cases. So if the setting is simultaneously, the combination will be either one or both of them together in one combination. If you say alternatively, they only get combined alternatively. So there is not a combination with both of those load cases together, but only one of them. And if you pick differently, you can decide how they are combined in, maybe 2 together and a third one not, but it's 4 more complex load structures. Next tab is design situations, and the design situations you have by default 1 ultimate limit state design situation and 3 serviceability limit state design situations, and this is in our case according to the Eurocode 0, and I'll tell you in a minute what it is about these design situations. Now the actions are combined. So you now see that the action number 1 is combined with action number 2 or without action number 2, and for the different design situations. So depending on what design situations you have, these combinations are being performed, and these action combinations then turn into so-called load combinations, where you actually then have the combinations of the single load cases again. So in this dialog, you go from left to right. Work yourself through in this manner direction. And now we can see that the combinations have been made according to the Eurocode 0, as we have defined in the base tab. And we can click on the assignment tab to see more details. So if we click on, for example, combination number 2, we can see that load case 1 self-weight is combined with load case 2 on the left. And we have additionally a combination with both of them and only on the right. As I said before, here in the action, if you pick simultaneously, it influences the load combination. For example, if I pick here alternatively and go back to the combination, you'd see that one of the combinations with both load combination number 2 and 3 is gone because, it's alternatively 2 or 3. Just go back because this is correct. They can they can be there simultaneously as well. And the design situation, you can now see that every combination is assigned to a design situation. And the design situation is an envelope for those load combinations. And we can see this in a bit when we calculate the results. We leave this dialog and move further down the tree to the loads. I want to define the loads by clicking on the member load icon in the toolbar, new member load, And now I'm asked which load case I want to use. I want to use self-weight. And I'm asked to which member number I want to assign this. So I click the pick icon and select those two members. And then I have to define the load magnitude. And for the load case 1, it is 2.5 kilonewtons per meter. And I could click OK, but then the dialog would close. And I have to assign 2 more member loads to my model. And that's why I click Apply and Next. And now some of the entries are being deleted. For example, the member number box. And I can now choose a different load case, imposed load left, with a magnitude of 5 kilonewtons per meter, and then use a different approach for the member numbers. So I click again on the Select Member in Graphics icon, and you can pick members and other objects, or you can draw a rectangle around them. And there are 2 different rectangles. There's a blue rectangle and an orange rectangle. And if you pick the blue rectangle, I'll show you. You can hardly see it, but the right member has been selected. If I do the same thing with deselect this. If I do the same thing by drawing right, it is not selected. So when the orange rectangle is used as selection, only objects that are fully inside that rectangle are selected. And if I do the same to the left and use the blue, also members that are only partly in that rectangle are being selected. Okay, so I want to use the left beam. Click OK and apply next. And the third possibility is to just use the member number. So we just assigned to member number 1 our post load. So member number 2 is on the right. So it just can just type 2 into the field and click OK because I want to leave this dialog, and it's created on the member on the right. So do a quick check if everything is correct. Seems good. And now we can calculate everything. And to calculate everything, there's also an icon here in the toolbox, Calculate All. I click on this, and now the model is calculated. First, the mesh is generated, and then, as you can see, all load cases and combinations are calculated simultaneously. So depending on what processor you have in your laptop or computer, the more you have, the faster the calculation is, because Rfem 6 uses parallel computing, and that way the computation time is reduced in comparison to Rfem 5, for example, and you get faster to the results. Now we want to inspect again the results. For example, the bending moment. I can get rid of the display of the loads by clicking on the Show Loads icon in the toolbar, since I only want to see the results for now. And I switch to the wireframe display so I can see better what goes on. And we want to switch to our design situation number 1. And now 2 graphs are being displayed, an upper one and a lower one. And that is because, as I said, a design situation is an envelope. So combination number 1, 2, 3, and 4 are combined in an envelope. And so depending on which location you are in the beam, every single combination creates a different set of results. And these are put together in an envelope and displayed. So you can see what are the minimum and the maximum values of, for example, the bending moment in this design situation. And yeah, so we want to see where these values come from. And we can do this by going into the table and going here into result by members and into the internal forces tab. And there we can see all results for the members in a table view. And I want to see, for example, where this negative moment of 35.88 comes from. And I search this value and I find it here. And I get a red arrow pointing to the location where I am if I click into the cell. And on the right, it says combination number 3 is responsible for this result. So let's check if this is true. Go back to combination number 3. And yeah, combination number 3, we have these 35.88 bending moment over the middle support. We can now try a different value, for example, the 26.77, so the field moment, and see where this comes from. So this is an entry here, and the program says that combination number 2 is responsible for this result. Let's check this again. And yes, this is the combination, leading to this result. Good. Now we want to check, for example, also support reactions. And we can see that if we go into the design situation back, that there are 2 arrows displayed. And like the internal forces, we have an envelope, so we have a minimal and a maximum value for the support reactions. And for example, if I display the loads again and go to combination number 3. So in combination number 3, we have the most load, and I think that this will lead to the highest value for the middle support of 77.42, and we can check whether the design situation also tells us that. So now we go to the result by node entry and go to the tab support forces and search for that value, and we can find it here. And as I said, combination number 3 is responsible for this. So that way you can go through the data and analyze how the results come together and which combinations are responsible for which results. we have done everything that we've been asked for this example. So let's go back into the presentation, and the next example we want to take a look at is the so-called Gerber beam or hinged beam. And this type of system is characterized by a hinge in the location where the bending moment is 0. And this leads to the fact that the center bending moment has the same value than the field moments. And if you recall the double span, two-span beam we analyzed before, there the center moment is bigger. So with the Gerber beam, the cross-section is more evenly utilized. Another advantage is that, for example, if you have a very large beam and you have to split it into multiple parts in order to be able to get it on the construction site, because a truck is not indefinitely long. And if you split a beam, of course, you have to connect it again back later on the construction site. And if you place that connection in the spot of the bending moment being 0, then you can simplify that connection by far. So this is a clever way of splitting beams in a good and in a good way, let's say. And if we want to see where this spot is, we can go into the Schneider-Bautabellen, which is a big book for engineers where there's a comprehensive it's a comprehensive book for every important information that you need as a civil engineer. And there's a table where we can find the information for a two-span beam with equal field length. There, the spot of the bending moment being 0 is at 0.1716 times the field length. And this value we are going to take over to Rfem 6, and we are going to try to model this Gerber beam. So let's go back, and I want to close those two models that we have already created to tidy up a bit. And I want to create a new model. And as you might have noticed, the Gerber beam has almost the same structure than the double span beam we did before, aside from the hinge. And there's a possibility to reuse existing models when creating a new model. So first I have to enter a model name and call it Gerber beam. And then I can select here existing model as copy. And now I have a drop-down list with all my projects, and I can find the model that I created, the two-span beam, select it, and if I click OK, all the model is opened in the background, and all the data is being retrieved and copied into the new model that I want to create. This is possible because by default, the two models that we created were saved into an existing project that I had. So if this is not the case with you, you won't find this this entry. But that's not a problem. We can use a different approach. We cancel this and we click on the Dlubal Center button, and then a new Windows opens up, a little bit big, make it smaller, and there we can organize our projects, for example, and we then again find the models that that were already shown to me in the drop-down menu. And if you do not see any of this, just make a right-click here on Projects and connect folder as a project. Now you are being transferred to the File Explorer, and you can navigate to the folder where the models that you have already created are saved on your computer. And if you do this, these models are available in this project navigator, and you can now reuse them in when creating a new model. So let's try this again. And reuse this existing model from our two-span beam. I then have to leave this drop-down menu by pressing the Tab key on your keyboard, and then the model is opened and all the data is being retrieved. And now I can pick, I have to pick the model type. Again, this is an information that is not being transferred, and I can click OK. And now we can see that the information of the two-span beam is being transferred to the new model. If you could not follow the steps I've shown right now, just take the two-span beam and alter the model. I just wanted to show you a little bit the Dlubal Center and the possibility to organize your models in projects. Good. So we have been asked to parametricize this Gerber beam, and I'm going to show you how to do that. So we go to Edit, and at the very bottom we find an entry called Global Parameters. And these global parameters are so-called like variables, if you will. And you can define these global parameters here and reuse them at different locations in the program. So what I want to define as global variables is a field length. Sorry. Just use the camel writing. And this is a length value of 5 meters. I reuse the field length that we already have. And then another global parameter I want to use is the Gerber factor. And this is not a length, but a decimal value or so-called float. And this value has or is 0.1716. And if I leave this, the 16 disappears. But this is just a graphical thing. We can go to the units and decimal places icon here down below and adjust the number of decimal places shown. And the program helps you and it displays a red triangle for every currently in the dialog used unit. And we have for floats only 2 decimal places showing. And if we select 4 and click OK, the 1/6 is being displayed again. Good. We click OK, and now the global parameters are defined. Now, the global parameters are only available through the Edit menu. And for the case that you forget where to find the global parameters, I want to show you how to find them again using the search. So just type in global parameters, and now you get the second entry is edit global parameters. And if you click on it, you'll end up in the dialog again. Another possibility is to add this to your toolbar. And I already did this because by default, this icon here is not shown. I can show you this. So I can click on Reset Menus and Toolbars to Default, and this will remove that icon. I can bring this back by going to the menu and under View, Customize Menus and Toolbars, I can search for the global parameters and just drag and drop wherever I like. I can put it down here. I like to put it here and close it. And now I have this button right under my nose for further use. And now we want to parametricize our model. And how do we do that? So currently, for example, the nodes are defined in an absolute way. So every coordinate has a value. It's not not parametric. And if we double click, for example, on the middle node, we can parametricize this coordinate by clicking on this right arrow, and we have different options. And I want to use the global parameters that we have just defined. And I want to use the field length, and I click OK and Insert. And what happens now, you get a small yellow corner, and this indicates that this field has an intelligence behind it because it uses a global parameter or a formula. But I'll show this to you in a second. So I click OK, and I want to edit the right button. And you might wonder why nothing changed when editing this node. That is because we entered a field length of 5, and this beam on the or the field length is 5 meters. So no change has been applied. But we'll see this in a second if we have once we have fully parametricized this model. Now we want to parametricize this node number 3 as well. And now I use the option Edit Formula. And here I can now, write a formula and define how the x-coordinate of this node is calculated. And the x-coordinate of this is 2 times my field length. And if I try to type, sorry, I need to use capital letters. If I begin to type, it finds this global parameter that we defined earlier, and I can click on it, and you can see the correct result of 10 meters because the field length is 5 meters times 2 is 10 meters. We click OK and OK again. Now we need to divide that beam because we need another node where we can where we can place the hinge. So we right click on the member, go to members, divide member, and then by distance. We then want to go just for now 1 meter. We want to parameterize this node that is going to be created later on, so it doesn't matter what value we use right now. So click OK. And now we double click on that node again, and we parameterize by using a formula. And I type in brackets 1 plus Gerber factor, close brackets, times field length. So what I wanted to do is it's now not showing. Move this a little bit and go back into the formula. So from the left, we have to skip the first field. So this is 1 times field length, and then a little bit of the second field. And this is the Gerber factor times the field length, hence this formula. And we get a result of 5.858. And we can double check this in the presentation. So we have, again, here 5 meters and 0.858. So yeah, we did it correctly. Click OK. And again, OK. And now we can try out this parametrization. And to make it a little bit more visible, I want to create a measurement dimension. And for this, I pick the nodes. And yeah, the measurement is the dimension is being drawn, but in the wrong plane. So I have to go and pick second plane, and now it's displayed in the right way. So we have a field length of 5 meters and the point of the hinge at 0.858 meters. And now we can go back into the global parameters and change the value, for example, to 4 meters. And if we click OK, the model changes. So the first field is now 4 meters, and also the point of the hinge has moved accordingly. So this is a nice possibility if you have similar systems and structures that you want to change really quickly, or try out the effects of different geometry or even loads. So these global parameters can also be used in loads and at different places throughout the program. So wherever you see like this field with this right arrow, you can click on it and use those global parameters and the formula that I've shown you. Now, the only thing missing is the hinge, and a hinge is a property of a member. So we double click on that member, and there's an option for hinges. And if I tag this, another tab appears where I can define the hinge. And I can define a hinge at the member start and at the member end. And yeah, I forgot where the member start is and where the member end is, but no problem. We see this graphic on the right, but there's a button here. And if you click on it, the graphic is displaced by this part of the model view. So this is the 3D workspace, and it is only showing the currently active or edited member or any other object. And we have here a display of the local beam axis system, and it goes from left to right. So the member start is at the left side. So we want to assign the hinge to the member start. And to do that, we have to create a new hinge, a new member hinge. And yeah, I want to make the hinge that the beam can rotate freely around the y-axis, the local y-axis. So this is the default values are okay. I click OK, and this hinge is then assigned to this member. OK. And now the hinge has been placed. I can make it a little bit bigger. And now we can calculate the model again and see whether the statement that the center bending moment and the field moment are the same value can be proven here. So let's see, for example, well, it is partly true, but this is just because the statement with the same bending moment values only is valid if the load is evenly distributed. And with this combination, we have a more load on the left side, so it only is applicable, or the statement is only applicable to for the right side. But if you pick a combination that has a even distribution of loads, we then can see that the results match this statement. And we also can see that with the bending moment, we have a bending moment of 0 at the spot of the hinge. So this worked out as well. And now we can try out the effect of the member length, for example. We have now a field length of 4 meters, resulting in a bending moment of 17 kilonewton meters. And we can now try if we increase this by 50% to 6 meters, what is the effect of this change? And we can now see that it has more than doubled. And yeah, this is an expected result. So yeah, you can try out something like this very easily via using these global parameters, and yeah, if you have a parametricized model. So now we fulfilled everything that we've been asked for this example. So let's jump into the last example that I'm going to show you. And the last example I want to show you is the two-hinged frame with a tie rod. And we have some information about the sections and materials. We are asked to apply a snow, a wind, and a temperature load case. And yeah, the analysis goal is the determination of support forces, internal forces, and deformations. So let's go back into the program and define a new model for this to hinged frame. I want to use the model type 2D again and create the model by clicking on OK. I want to show you another way of creating materials and sections. So we have defined nodes in the table, but you can also define a material directly in the table, and you even can search for materials in the table. So let's search for S235. So like in the dialog with a name box, you can search here in the cell, and I pick the Euro code 3 steel, and I want to repeat this for the HEB 300 cross-section. And for the tie rod, I don't know what to search for. That is why I go back into the section library and I select round bar, and the tie rod has a diameter of 30 millimeters. I click OK. And if I'd known that the section name is round space 30/H, I could have typed this in by myself. But yeah, as I told you, there are always different possibilities to define objects. Now we want to define the members, and as for, or like for the double span beam, I want to use the continuous simple option here, and this is okay. And now I can draw. We have a column height of 5 meters, and the top of our frame is at 8 meters in Z direction and 5 meters in X direction. I now hit escape because I want to quit and show you something else. So the structure we are supposed to analyze is a symmetrical structure, and to speed up the process of modeling, you can use some of the manipulation options that we provide. So if you select geometry and you right-click on it, there's an entry manipulation. You can move and copy elements, you can rotate them, you can mirror them or scale them. And I want to mirror this geometry because it's symmetrical, and I want to create a copy, and I select YZ plane, and I pick a point here, the top point, click OK, and the other half of the structure is generated automatically. I then need my tie rod, and then I have to change here the section for the first time because now we have 2 sections. Click OK and connect those 2 lines together. Next step are again the nodal supports. I use the icon here in the toolbar. Hinged is the one I want. I pick the nodes, draw a rectangle around it, click OK, and OK. So I made a mistake. I created this tie rod without changing the member type. So it is a tie rod, so it is supposed to have only tension, And there's a member type for this called tension. And this member type fails once it is asked to get compression. It says no. I have then an internal normal force of 0 instead of a value. So it'll fail if it would get compression. So now we rectified this. We can barely see those nodal supports, so let me make those a little bit bigger. Now we have to define the load cases. We do not need a self-weight, that's why I'm going to deactivate this and rename the first load case to snow and pick the correct action category. Then I create a new one for wind and a third one for temperature. And if we now go through this again, we can see some interesting stuff. So if you go to the action combinations, you can see that some of the entries are grayed out. And that is why, that is because the program detects that some of the action combinations are duplicates of other combinations. For example, the action combination 25, 0.2 times action number 1, delivers the same result as 26, 27, and 28 because the factor for action number 2 and 3 are always 0. So the program prevents that unnecessary load combinations are being created. And we can see this because if we go to load combination, the list is shorter than the list of action combinations. Usually it's the other way around, but in this case, it's like this. And all the load combinations are again assigned to the design situations again. And another interesting thing I wanted to show you is the combination wizard. So the different load cases are being combined, and you can see that there's a leading load with a security factor, and then you have the other two load cases with a psi factor being combined. And this leading load changes, or every load case is one time the leading load in a load combination. So the combination wizard takes up all the work for you to create these combinations according to the standard that you've chosen in the base tab. Now let's define our loads. We have again member loads, and we start with a snow load. And the snow load is 1 kilonewton per meter. And we want to assign this snow load to the roof members. And as we can see down here, there are different possibilities to apply such uniform load distributions to our member. And for snow loads, usually the projected length is used like this. So we have to change the load direction. Apply and next. We go on to the wind load case, and we want to assign this to all beam members. And the value of each of these beam members is also, or the load magnitude is also 1. And here we have to change something else for the load direction. So usually wind loads are applied directly to the member. So we have to use the local axis system instead of the global axis system. And the load direction in Z direction is correct. And the load magnitude also. So we click apply and next. And finally, we have a temperature load case, and therefore we need to change the load type to temperature change. And the temperature change is 35 degrees Celsius. And I want to assign this load also to all beam members. We click OK, and let's check whether we have applied all loads correctly. And we can see that we made a mistake when applying the wind load, because the wind comes from the left, and so there should be suction loads on the right side. So we have to flip over these loads, and we can, for example, do this by going into the table in the section loads and pick here the tab member loads, and we can create a second load and apply this load to these members number 4 and number 3. So I change here the value to 1 and 2 for the positive direction, and now I type 3 and 4 and change this value to -1, and now it is flipped over to the opposite side. If we go back into the dialog again by double-clicking on that line, we see an option that we can display the load on the opposite side, and this way it's displayed a little bit nicer, I think, because it's more clearer that it is a suction load coming from the outside. Now we can calculate everything and inspect the results. Here again, you can see real nicely how the parallel calculation works, and that it calculates very quickly. So let's go through the load cases. We have a snow load, and it is deforming our structure, and I'll just change the display to wireframe, and you can see how the structure is being deformed, and I would expect that our tie rod is now under tension. I can check this, and this is correct. The tie rod is under tension, so it's a plausible result. We can then try to inspect the wind load case, and the wind load case, it drives our structure to the right, and in this case the tie rod would be under compression, but we decided that this member is of type tension, so it should fail in this load case, and let's check if this is true. So the normal internal force should be 0, and this is also the case. So yeah, it is a valid result. And the last one is the temperature load case, and here we have a deformation. Again, like with the snow, the tie rod is under tension. Good. Let's have a look at the support reactions. And I want to show you something with the wind load case. So the wind comes from the left and drives the structure to the right. And so it creates a moment around the center of the structure. And that leads to a force pair being like a compression support reaction on the right and a lifting support reaction on the left. So yeah, this is interesting because you might need to design the connection for the left side accordingly. So it can bear not only compression forces, but also lifting forces. And if we go back into, for example, a combination with wind and load case number 1 and 2, so snow and wind together, we see a different image. So if you put those two load cases together, you can see that there's a small compression reaction force on the left and a bigger one on the right. So yeah, we have done everything that we've been asked for. So let's go back. And yeah, you've earned yourself a break.
Okay, so the break should be over, and that means that we start with the second part of today's student training, Introduction to Member Design. Yes, I hope that you could enjoy the break. You already learned very much about the program in the first part of this student training. So now you have a good overview how the program looks, and you are also already able to use it to model the system and calculate it. In the second part, we will have a look at a few more examples, and that will be a good opportunity for you to practice what you already learned. So also in the second part, we will model the system. And yes, I think that can be a good practice for you. But we also want to have a look at a few more functions and topics in this second part. Okay, so let's start with the first example, and that would be an ideal truss structure. So maybe let's first have a look at the structural system. We have members with the section HEP 300, and material is steel S235. So all members have the same section. This truss structure has a length of 9 meters at all, and these triangles do all have the same, or the members of the triangles do all have the same length, which would be 3 meters. That also means that the angle between these members is always 60 degrees. So it is 60 degrees here at the top and also at the right of the triangle. So in sum, it would be 180 degrees. Okay, So the word ideal trust structure has a special meaning, and there are some conditions that have to be fulfilled that it really is an ideal trust structure. The first condition is that all members in the system have to be connected with hinges at the member ends, or yes, at these nodes. So that means that there are no bending moments which can be, which can go from one member to another. Also, it is important that all members are straight. Yes, that's definitely fulfilled. And there cannot be any imperfections, and as well, there cannot be eccentricities. So we don't have this in the system, so that would be fulfilled. It is also important that we only have nodal loads. Yes, that's the case. We have 3 nodal loads. It's not completely symmetrical. The left and the middle load are 10 kilonewton, and the right one is slightly bigger with 20 kilonewton. One last thing for the ideal truss is that we only have normal forces inside the members. So there are no internal forces, bending moment, and no vertical forces, only normal forces, so compression or tension. And because of this fact, we want to use a new member type, which is called truss only N. But we will see this very soon in the program. Okay, let's have a look at the tasks. Here we want to determine the support forces and internal forces. Also, we want to determine the null members, which means these members which do not have either tension or compression. Also, we want to decide which members to have tension and which members are loaded in compression. Okay, now we can switch to Rfem. Here I opened the program. I have a blank new model, nothing inside here except one material and one section that I already defined. So that's the material we need is 235 and the cross section HEB 300 that we want to use. Let's also have a look to the base data dialog, which is a really important dialog box in Rfem. And here we choose the type of model 2D XZ plane stress. And that means that we only model in a 2D plane, and also the results like internal forces and deformations and so on are also only in this plane of the model. So we don't have any results outside of the plane. Okay, we don't have any add-ons activated right now, except the load wizard, but yes, we could also deactivate it because we will not use it today. Okay, and now I will rotate the view. We can do this by clicking on -y at the view cube so that we get a better view on our modeling plane. Okay, the first member, which would be the first diagonal of the truss, we want to model by the function single general new member. By clicking that, we get into the dialog new member. And here we said that we want to choose the member type trust only N. Okay, let's select this. And as you can see, the image on the right side has been updated. And now you can see or you get an idea about how this member type works. So if I go back to Beam, you can see that there are all internal forces from the 6 degrees of freedom that this member type has, but the truss only N does only consider normal forces as shown in this image. Yes, as you can see, there are many different member types, and sometimes you want to be clear about what they do in detail. And for this, there is a very useful help function, which you can find in almost every dialog box in the program. And you find this at the left bottom side of the dialog box, the help button. You can also press F1 if you want. And if I do so, we get to the Dlubal website, and the direction is the correct chapter of the online manual. So by clicking there, you instantly get to the right side, and that's very useful. So here you can read how this particular member types work. For example, the member type trust only N that we want to use, and you get a small explanation about this member type here. And for example, there's also a webinar where this member type is shown and explained in detail. Okay, I will close the browser. We go back to the program and let's have a look to the tab section. And here it's already chosen correctly. We want to have the HEP 300 with the material as 235. We can apply this, and now we can model the first diagonal. So we want to do this with the function or by the input mode length and direction, because we know that this member has a length of 3 meters. And we also know the angle. As I said before, it's 60 degrees from the x-axis. But in this case, it's always located from the z-axis, so we have to add an additional 90 degrees. So that would make 60 plus 90, which is 150 degrees. And now we already see at the mouse button that the angle of the member is correct. So now we can click into the coordinate system and create our first member. Okay. And the second member, we want to create this member by rotating the first one. And also here we can use the knowledge of these 60 degrees. So I select this member and choose the option rotate selected objects. So now we want to rotate this member by 60 degrees, and we want to create a copy because we need a second member, and this member should stay where it is. We also have to choose a rotation point, which would be the upper end of this first member. Okay, and now we already have the second diagonal. Okay, for the other diagonals, we can also use the copy or move function. So I selected everything again, go to copy, and here we want to create a copy, of course, and not only one, we want to create two copies. If you have a look into the image on the right side, you get an idea what it means with these two steps. So this object is not copied once, it's copied two times. Yes, and that's exactly what we need for the rest of the diagonals. And now we have to choose the displacement vector. We can type in the values easily because we know that this dimension are 3 meters and we want to copy it step by step by 3 meters. It would also be possible to select 2 points. Let us do this. And then you see, yes, that was correct. It's 3 meters. Okay, we can apply it. Click on OK, and the other diagonals are created. Now we also want to create the upper and the lower chord. And I will do this graphically by creating a new member. It should also be the truss member type and the same section as before. Okay. And here I select the start and the end points of the chords. And yes, now you can see that it is one member only, and this member is not divided at these nodal or at these nodes of the diagonals, and that's not a problem, but we want to divide it afterwards. And there's a useful function called connect selected lines, members, and surfaces at intersections. So we can click on this function and simply select everything. Yes. And now the chords are divided at every node which lays on this member. So yes, that's the result that we wanted. And yes, now we want to prove if the geometry is correct. And for that, we can use the linear dimensioning. Okay, linear. And we want to prove the length of the diagonal. So let me choose this diagonal. And here we will have to select the second plane so that we can see the eccentricity of the linear dimensioning. Okay, that are 3 meters, that's correct. And now we want also to create a dimensioning here at the bottom chord. And yes, we see that the geometry is correct. It's 3 meters, 3 meters, and 3 meters. So at all, these are 9 meters from left to the right side. Okay, now we do have to define the supports at the left and the right end of this truss. And therefore, I first want to get rid of this coordinate system, which is a bit annoying here in this case, because I want to define the nodal support. And yes, the coordinate system makes it harder to see the support later. And therefore we can yes, we can move it away by choosing the display navigator. So you have to choose the tab with the eye symbol, and here you basically can select every possible object at the working plane, and you can select if you want to make these objects visible or invisible. And in this case, we want to make the axis system, the global coordinate system in the 0 point, invisible. And as you can see, it's away, and we also can activate it again if we want. Okay, and now we can define the nodal supports. I click on this symbol for that. And here we want to define a free rotation about the y-axis, and everything else should be fixed. So let's have a look into this definition of the nodal support and see if it already is correct defined. So here we see that the deformation or the translational support in global X and in global Z direction is yes, fixed. That's correct. And the rotational support about the y-axis is free. So that's exactly how we want the nodal support to be. So that would be correct. You can also see that some of these degrees of freedom are displayed with a gray box, and that is because we are in the 2D plane, and there you only have 3 degrees of freedom, and in the 3D plane we have 6 degrees of freedom. So these boxes would also be possible to define, but in this case we only have the 3 degrees of freedom. Okay, now we can define the nodal supports here. Let's make these supports a bit bigger so that we can see it better. This is possible by right-clicking it and increasing the display size of the nodal supports. So yes, something like that. Like that should be okay. For the right side, we have to change the support a little bit, and therefore we can create a new one. And this support should be deformable in global, I guess, in global X direction. So you also see that the symbol of the support reaction changed, so that you get a graphical overview how you defined the support. Okay, that is how we want it to be, and how it's set in the task. Now the loads are still missing, so we want to define them, and loads always have to be defined in or within a particular load case. And at the moment there are no load cases because yes, I opened up an empty model without any load cases. So we can create a new one by clicking on this symbol, but we can also choose it from the data navigator at load cases and combinations. Load cases, right click, and we can choose new load case. Okay, so now we got into the load cases and combinations dialog box, and inside the tab load cases, there has been created one new load case for us, and we want to use this load case. Let's give it the name design, design loads, because we don't want to consider any standard like Eurocode or something else, and we don't want to build our combinations. We just want to apply the loads from this example and calculate it like it's like it's done in the university, for example, at technical mechanics also. Okay, so we have this load case, design loads, and here it is very important to deactivate the self-weight, because at the start I said that the ideal truss structure can only have nodal loads and no member loads. And yes, self-weight is a member load. So if we would let this activated, then it wouldn't be an ideal truss anymore. So we don't want to consider the self-weight. Okay. And now we can create our nodal loads within the load case design loads. New nodal load. We want the load type force. We want to define it at the global coordinate system, and the load direction should be in global Z direction. That's all correct. And the value for our nodal loads are 10 kilonewton. And at the top right part of this dialog box, we can assign this load to one or also to multiply or to multiple nodes. So we can select the first two nodes, the left one and the middle one of the upper chord, and click on OK. We can also click at Apply and Next, because we need to define the third load, which is a bit bigger. So as you can see, the first two loads already have been created, and now we can create the last one and select the right node. It's also not a problem if you forget to assign this load to a node, because if you click OK, then you get this info box which says to you that yes, at least one node has to be assigned, and this way we can also assign this node afterwards. Good, now we have modeled everything that would be necessary. So we have the members, we have the supports, and the loading as well. If we calculate this now, I want to change some things at the view so that we get a better overview for the results. First of all, I want to choose the wireframe model. So in this model type, the members are not displayed with their original thickness or with their cross-section. No, they are just displayed as lines or as wires. We also want to make the dimensioning invisible, so we can choose that in the display navigator, and you will find this under guide objects and dimensions. So let's deactivate the dimensions, and now I think we have a good base and can calculate this load case. This can be done by clicking on Show Results. As we don't have results at the moment, the calculation will start automatically. Or we can also click on Calculate and calculate current loading or calculate all. In this case, it is the same, as we only have one load case. Good. So first of all, I would like to prove the equilibrium, and therefore we can have a look at the table, static analysis, and here we choose the drop-down entry overview. Normally it's automatically selected like that. So, and here we see the sum of loads and sum of support forces. So we have a sum of loads in Z direction of 40 kilonewton. And yes, that's correct. We have 10 plus 10 plus 20 makes 40. And we also have a sum of support forces in Z of 40 kilonewton. Let's show the support reactions by activating them in the results navigator. And here we see 16.7 plus 23.3 makes 40 kilonewton in sum. So we have a deviation of 0%, and that means that the equilibrium is fulfilled. So far so good. And we also see the deformation of this model. The deformation is displayed by these purple lines. The maximum deformation in this case is 0.1 millimeter, as you can see here. And it's displayed much bigger, and that's because the factor for the displaying of the deformation is automatically chosen so that we will see something. In this case, it's 6,000, and the original deformation would be the factor 1. We can select this, and now we won't see anything because 0.1 millimeter is extremely small, so we have to zoom in very, very much to actually see this deformation. Okay, so yes, maybe let's increase the factor again so that we can see something. And yes, the support reactions, or yes, the supports do also work correctly. So the left support holds the structure in X and in Z direction, but a rotation about Y direction is possible, as we can see here. And right support also allows a deformation in X direction. So this node and the members which are connected to this node have the possibility to move into this direction. And yes, that's exactly how we wanted it to define. There is also the possibility to change the view, or to change the way how the deformations are displayed. And therefore we can have a look to the lower part of the results navigator and go into the chapter deformation members. And here we can choose, instead of lines, which are these purple lines, we can choose, for example, section colored. And yes, that's also a very good option to make the deformations visible. And these colors also have a meaning. If you choose in the control panel the tab at the first tab with these colors, you see the meaning of these colors. So everywhere you can see a blue color, the deformation is 0, like here at the left support. And the red color means that the deformation has its maximum at this place. Okay, now we want to have a look at the internal forces. And if I'm correct, then there should only be normal forces, and the other internal forces should all be 0. So let us prove this. First of all, we have a look at the normal forces and can see, yes, there is a normal force displayed by these red and blue diagrams. And now we can have a look at the other forces. So we don't have any vertical forces in y direction, also not in z direction. We don't have a torsional moment, and we also don't have a bending moment about y-axis, and the bending moment about z-axis is 0 as well. So I'm right, luckily, or also not. We only have normal forces. If you wonder what these two colors mean, that means if it is a tension or a compression force. So the red colors are positive or have positive values, like here, 17.32. And that means that it is a compression load. So positive values are always, positive values are always tension. So the red color means tension. And the blue color is for the values with a negative value. And this means that we have compression inside this member. Okay, that would be everything. In this moment, I recognized that I forgot something to model, and this has been the vertical members of the system. So if we have a look back into the PowerPoint presentation, we can see that, yes, I should have modeled these members as well. I'm sorry, I forgot them, but that's not a big thing at all, because these members don't get any normal forces. So that would be the second task of this example, determine the null members. And in this case, that would be all the vertical members. And as you can see here, these members do not have any compression or tension force. So the normal force is 0. And yes, if you have a look at the internal forces N at the other members, you will recognize that these internal forces are exactly the same like in the program where I forgot to model the vertical members. So that means they do not have any influence or any impact to the results. We can let them away and it would not make any difference. So let's, for example, have a look at this value. It's 17.32 kilonewton, and it's a compression force. And maybe let's have a look at another value, like yes, this right diagonal, which would be minus 26.94. And if we compare this with the program results, we also have here the internal force N 17.32. And at the diagonal, we also have the value minus 26.94. So it's basically exactly the same. Okay, that would be everything for this example. So let's go back to the presentation and let's have a look at the next example. The next example is a suspended single span beam. So in this structure, we have two different types of beams. First of all, we have this bending beam, which is colored blue. And yes, this bending beam has a relatively big length or span width with 5.5 meters times 3, which makes 16.5 meters. Yes, that's relatively much, and probably this bending beam would not be able to hold this loading of 15 kilonewton per meter. And because of this, there is an additional structure over this bending beam. This is colored red, and these are truss members which support this bending beam at 1/3 of the length and 2/3 of the length of the beam. Yes, that would be the system for the truss members. So these are the red colored ones. We have an IPE 200 now, and the beam stays an HEB 300. Also, the material will be the same as before. The task here is to determine the support forces and the internal forces. Also, one thing that I want to mention, we this time have two different types of supports. So at the left side of the bending beam, we have a rotational support, and at the right side, we have a rotational support with the possibility to move in global X direction. But for the truss members, we don't have this freedom. The two supports on the left and the right side for the truss members is only or does only have the rotational freedom, but it's fixed for the deformation in X or Z direction. And that is also necessary because if you imagine that this is like a rope, then you will get very decent tensions on this member. And if we would make the deformation in X axis free, then this rope would simply go to the middle of the structure, and yes, the function of this support would not be there anymore. Okay, then let's try to model this structure. And therefore we can delete everything we modeled before so that we have a clear model again. Yes, that working plane is clear again. Yes, I would like to show the coordinate system in the 0 point again for a better orientation. So we can choose this in the display navigator and activate the global coordinate system. And yes, maybe we can also activate the dimensions again. So that should make it. First of all, I want to create the bending beam with a length of 16.5 meters. And yes, here we have a little problem because we only have these points in 1 meter step. So of course we could configure the working plane or the work plane and reduce the grid point spacing to 0.5 meters, for example. But that's not even necessary. We can also make this much simpler. And yes, therefore we create a new beam. This time it should be a member type beam again with the cross-section HEB 300 and this material. So that fits, and we can click on OK. This member should start in the 0 point of the coordinate system. And yes, now we don't select the right length. We select any length. So for example, yes, I can define a 2 meter beam. And now we can configure the length of this beam afterwards by changing the coordinates of this node. So here we don't want to have a coordinate in x direction of 2 meters. We want to have our 16.5 meters. So in solution, the node moves to the right side. Now it's at 16.5 meters in x direction, and the beam automatically also moves to this node because the beam is defined at a line, and this line is defined through these two nodes. So if I change the coordinates of the node, the beam will automatically go with the node. So that's a simple method to quickly create this beam without changing the working plane grid. Okay, now we want to divide this beam, and we can do this by right-clicking members and divide member at intermediate nodes. We need 2 intermediate nodes, each at 1/3 of the member length. So we have to select the number 2 as number of intermediate nodes. And in this case, we don't necessarily need to really divide this member so that we have 3 members. It would be better to have this one big bending member. And in this case, we can choose the option create on member nodes with dividing member. Okay, let's click on OK. And now you see that these nodes have a blue color, not like the other nodes with the red color. And that means that it's a node type of, or a node of the type on member and not a standard node. And yeah, the positive aspect on these nodes is that the member does not get divided. So we have one big member left. Okay, maybe we can switch to the solid model again so that we see better what we modeled. And yes, it looks okay. And now we still have to model the upper part of this construction, which would be the truss members. And yes, for that we can copy these nodes in Z direction. And yes, we will do this first of all for the intermediate nodes. And these nodes have to be copied 1.4 meters upwards. Okay, let's copy them. Yes, we want to create a copy, but we only need one step. And in this move or copy function, we do have another really helpful option, which we can find at the second tab, numbering and options. And here we can activate the option step length. And this function does the following. So it creates objects between the base object and the copied object. And this could be very helpful in our case because we need to create a truss member between the nodes on this bending member and the copied nodes. So we can activate the option link nodes with member. And now we have to choose a template member. In this case, we don't have the right member in our model, so we can create a new one. The member type should be truss only. No, it should be the normal truss. Yes. And therefore, we want to create a new section, which would be the IPE 200. All right, let's create the IPE 200. Yeah, normally we could choose this cross section from the section library, but we can also make this much quicker by typing in the name of this cross section, and then we get some sections we can use. And I would use this one, which is an IPE 200 as we need it. Okay. And now we can confirm it and create it our template. One thing I probably forgot to do was the displacement vector. So we want to displace the node 1.4 meters in negative Z direction. So it has to move to the top, and the positive Z direction is directed to the bottom. So in this case, we would type in minus 1.4 meters. Okay, and as you can see, we did two steps with one function. First of all, we copied the nodes, and the second thing is that we already created these truss members. Yes, which is really helpful for us. And now we can copy the nodes at the end of the member. These nodes have to be copied 1.4 plus 0.9 meters upwards. So it would make 2.3 meters at all, and also in minus direction. Yes, we want to create a copy with one step, but this time we don't need the step links. Okay, and yes, let's create the missing truss members relatively quickly. Yes, it's truss IPE 200. Okay, that's correct. And we can create these members graphically. Okay. Now I would like to prove if I correctly assigned the write cross-section to these members, and therefore we can choose in the display navigator relatively at the bottom, we can choose colors of rendered objects by object property, and then we can choose by member, and there we don't want to render the object color by material, so everything is the same material. We won't see any difference. No, we want to display it by section, and as you can see, we have two different colors here. And at the right side, in the side of the control panel, you can see what these colors mean. So every member with the light blue color is an HEB 300. So that's our bending member. And every member with the yellow color is an IPE 200, which are the truss members. So that would be correct. Yes, we correctly assigned the cross sections. Good. Now we want to define the supports. It's basically the same thing as before. Yeah, let's choose again this support for the left side of the bending member and for the left and right side of the truss members. We can again increase the size of these supports, and for the right side we need another support type with or without the support in translational global X direction. Okay, and we also can define this here. Now we have our supports, and yes, one thing is missing, and this would be the loading, and therefore we want to define a member load. So new member load, and the load type should be force. There are also many other options like moments or axial strain or displacement, like temperature and many other things. And yes, I think it's good to say this again. Also here you can use the help function if you are not clear about what this member load type means. And here you get a short explanation about these member loads. And yes, it's again at the online manual, which you can find on the Dlubal website. Okay, so we want to define a member load which goes in the direction Z. So that would be okay. In this case, it's unimportant if we choose on true length or on projected length, because the bending member is horizontal and this would not make any difference. The load magnitude is 15 kilonewton per meter, and we want to assign it to our bending member. Okay, that should be it. Let us confirm. And yes, in my opinion, the load is displayed very big, so we could reduce the size of this load. So I think it's better this way. Yes, and now the system is ready. We have loads, we have the members and the supports, and can calculate it again. Okay, and yes, let's activate the wireframe model again. Maybe we can deactivate the loads so that they are not shown to get a better overview. And yes, good. First of all, we want to have a short look at the global deformation. So yeah, basically the load is directed in positive z direction. So yeah, it's relatively logical that the system will also deform in positive z direction as it does. That looks okay. Now we already have a much bigger deformation of maximum of 46.5 millimeters. Yes, that's much more than in the example before. And yes, let's have a look at the normal forces. And as you can see here, the normal forces inside of the truss members are relatively big, with 467 or 68 kilonewton. That's a big tension, and this tension, or for this tension, we need the support which holds the member in X direction. So we can see that the support reactions are that big as well, especially the horizontal support reaction. Okay, yeah, let's have a look at the bending beam, and here would be interesting the vertical forces Vz, and we can see that this vertical force is jumping at the points where the truss member is connected. And in this case, it would be interesting to know the values here, but as we can see, only the values at the start and the end of this member are shown. But it's not a problem, or it's easy to make the values at other points of the member visible. And you can do this in the lower part of the results navigator at members, and then you can activate the option all values, where you get more values. And as we can see, we have a jump of 41.25 plus, or in addition with these 34.26, which makes in sum something like 75.5. And this normally should be exactly the normal force inside of this truss member. So let's prove this. And yes, that's correct. The normal force in this truss member is 75.5. Okay, yes, that seems plausible. And there is one thing, or one more thing, that I would like to show at this system, and that is a very helpful function you can find in the right-click menu of the member, and this function is called result diagram. By clicking on the result diagram, you get an additional dialog box, and here you can choose more than one results which should be shown for this member. So at the moment we are looking only at this bending member that I selected, and for example we can show the global deformation. Okay, that's okay. Internal force N is 0, so yes, that's not interesting right now, so we can deactivate it at the left side. But it would be interesting for example, to see the vertical force as well as the bending moment. And the great opportunity in the result diagrams is that you get multiple result diagrams in one view. So normally if you select a result type, you can only see one result type at the same time. And inside of the result diagrams, you can see more different result types. It's also possible to create such a smooth range by double clicking on this scale, and you can also change the size of this smooth range. And as you can see, the smooth range it makes the intermediate value in this range. Okay. So we can also delete this smooth range again by right-clicking and selecting delete smooth range. And another useful function would be the printout. That means it's possible to print or to directly print this graphics into the printout report, or you can also print it with your printer or print the graphics to a PDF file. So yes, in my opinion, that's a really cool feature which allows to make your results more or to allow a better visibility of your results. Okay, that should be everything. So the task for this example was determine the support forces and internal forces. I think that we have done this. And yes, in addition, you learned a new feature called the result diagrams. Good, then let's have a look at the next example. And this would be a generated truss structure. So yeah, as you can see, this structure has a few more members, so it would be kind of or would need kind of a longer time probably to create this model. But there's a very simple way to generate this whole model, and that would be the function called blocks. And yes, in this example, we want to have a look in detail what these blocks can do, and yes, how they can help you if you are trying to model a structure. And yes, I think we don't have to explain very much about this, so let's jump right into the program. And also here we can delete everything we modeled before. So the blocks function can be found by clicking on this blue symbol right to the Dlubal center. Or basically you can also find it inside Dlubal center. But yeah, this time we want to open the block manager directly. And yes, then the block manager has been loaded. And here you find a big or many different blocks, a big library of blocks with different categories, like for example beams, trusses, bracings, or for example, let's for example have a look inside bridges, which I find relatively interesting. And here you get structures which are already have been created, and you can use this for your own projects, which can be very helpful. So in this case, we would like to generate a truss. So let's have a look inside the trusses chapter. And in this case, it is a 2D truss. And yeah, let's look, let's see what we have here. That's a very big amount of different blocks. And for example, this last one does look like the one from the example, so we could use this as a blueprint. Okay, to load this block inside the program, we can double click it. And now the program is asking to change the model type to 3D. So it means that this truss block has been created in a 3D model. And yes, we will have to change to 3D to be able to implement this block. It's not a problem in this case, so we can click yes and change the model type to 3D. And now we get a new dialog box for this block. So on the right side, you can see how this structure is looking at the moment. And you also have the dimensioning for this structure already implemented. In the first tab, so in the main tab, you can choose the position of insert point and the insert point itself. In our case, we want to insert this block at the coordinate 0 point, so everything can stay as it is. And we want to have a closer look at the tab structure. And here we are able to change the geometry and the materials and the sections of this block, which is a really mighty feature in my opinion. So now we can type in the lengths and heights that we have in our example. So in the example, the truss had the lengths for L1 and L2 of 3 meters. So we can type in that here. And as you can see, if I type in these values, the block immediately changes its geometry. So the height was 2.5 meters. Let's change that to OK. And now we have to define the cross sections. For the upper and the lower chord, we want to use an HEA 300, which we have to create first of all. Okay, let's type this section in. HEA 300, for example. Yes, that should do it. The bottom chord should be in HEA 300 as well. And the diagonals should be an IPE 160. We don't have this cross section yet, so we need to create it as well. Okay, I will make that really quick because it is kind of a repetitive work. And the post should be an HEA 160. So let's also create this last section. Okay. And here we can also define the supports for the left and the right side. In this case, yeah, it should be okay. Maybe we can change this just a little bit because we want to have a rotational support also around or about the global x-axis. Yeah, we can activate this checkbox so that the system is rotationally supported. Okay, let's change this, and yeah, this has been done. And now we can implement this block into our Rfem 6 file. First of all, I want to show one option of the block, and that would be the last tab. And here you can see the source code of this block. And by clicking on this symbol at the left bottom side of the screen, you can make this source code editable. And here you can theoretically program your own blocks. If you change this source code, you can change the structure input for the model, and you can also define how the geometry has to be generated. So yeah, in my opinion, a very mighty feature. And especially if there are always, or if you are working in a company which always have similar structures to calculate, then such a block function can be very useful because you define this block once. And yeah, after you have done this, you can always use this block and be much faster with modeling. But now let's generate this block by clicking on OK. And as you can see, we have this whole structure in Rfem 6 now. We can also show it as solid model. And there's one thing we want to change for this example, and that would be the diagonals and the posts. At the moment, these members are beam members. So the member type is beam. And these have a hinge at the member start and end point, as you can see here. So the option hinges is activated. But it would also be possible to make this much easier and define these members as the member type truss. And then the hinges are automatically generated. So, okay. For this, or to change the member type, we would have to select all posts and all diagonals. And therefore, we can use the option which can be found in the navigator views, visibilities. And here we can activate a visibility, and we only want to show the diagonals and the posts, which would be these two sections. And now we can simply select everything we see, and yeah, therefore we have selected all diagonals and posts and can change or edit them to the member type truss. Okay, let's show everything again. And yeah, now you learned how to use the block feature. I hope that you find it as useful as I do. And that would be everything I wanted to show in this example. So we can go to the next one right now. Okay, so now we want to leave the conventional part of this student training, and we will have a look at a bit different topic, which is the second order theory and its influence on the results. Until now, we always calculated geometrically linear, which means that we calculated with the first order theory. So in this case, the deformation of the system has no influence to the results or to the internal forces. The results are calculated at the undeformed system. In second order theory, this is a bit different because here the results are calculated at the deformed system, and this can lead to the point that the internal forces are getting bigger because of the influence of the second order theory. Of course, the calculation with first order theory is much simpler and easier, but it's not always allowed or permissible to calculate with the first order theory, because if the influence of the second order theory is getting too big or becoming too big, then it has to be considered. Okay, for this example, we have a pretty simple model, which is a vertical beam, a fixed column with a length of 10 meters and 2 nodal loads at the upper end of this column. Okay, let's go back to Rfem 6. And first of all, we can deactivate the visibilities. We can also delete the block, which you can find under special objects and blocks. So right click and delete. And we can start again with a blank model. Let's also remove the control panel. We don't need this right now. And we don't want to go into detail with modeling, so I will do this relatively quick. We want to get results relatively fast and have a closer look at the results. Okay, so let me quickly model the column. We use the member type beam and a section HEB 300. That's okay. And the column has a length of 10 meters. We can also add linear dimensioning in the second plane. All right, 10 meters. And we can add the fixed support first of all. So it's supported for every degree of freedom in this case. And the nodal loads. Here we can make this a bit easier, so we don't have to open this dialog twice. We can use the load type components, and here we are able to define both loads in one step. So we have 10 kilonewton in horizontal direction and 100 kilonewton in vertical direction assigned to the head node. Okay. That's it. And now we want to change the settings so that we can calculate with second order theory. Therefore, we go inside the load case. So open this dialog, and we want to copy this load case. We can do it by pressing this button, copy selected load cases. And in the second load case, we want to consider the second order theory. So I give a hint for that. Second order theory. And as you can see, we have to choose this in the static analyzer settings, and we have already 3 templates for that, which is first order, geometrically linear, second order, or third order, which are large deformations. So we want to choose second order here, and we can also have a closer look inside the static analyzer settings. Let's configure these settings and see what we can modify inside here. So first of all, we can choose the analysis type and the iterative method. Newton-Raphson is okay in this case. We can also increase or decrease the number of iterations or the maximum number of iterations, as well as the number of load increments. This option is only available for second order or third order theory. For first order, for the geometrically linear theory, it's not available because there we don't have to do the iterative process. Everything can be calculated within one iteration or with one calculation step. So no iterations needed. So the standard settings are well chosen already, so we don't have to change anything. Okay, and we can confirm this. So now we have these 2 load cases, both with these loads. Now I want to show both load cases at the same time. For that, we can create a new window, and we can select a tile vertically, for example. And then we have the system 2 times, and at the left side we can choose the first load case with first order theory, and on the right side we can choose the second order theory. And now we will start the calculation. Okay, that went really quick. And first of all, we want to have a look at the global deformation, which is 63.5 millimeters for the first order calculation. And for the second order calculation, we have a slightly bigger deformation of 68.7, but it's not that big of a difference. Okay, now let's see the internal forces My, which is the bending moment, and especially we want to have a look at the bending moment at the lower or lowest point of the member. So we choose My in both windows, and here we can see that after first order theory we have a bending moment of 100 kilonewton, which is the horizontal load of 10 kilonewton times the lever arm of 10 meters. That makes sense. But now, if we calculate with the second order theory, we have a bending moment of 106.9 kilonewton meters, so it's slightly bigger. And this is because the internal forces are calculated at the deformed model. So let's show the deformation again. And we have a deformation of 68.7 millimeters at the top. So now the vertical load also has a lever arm, which means that we get an additional bending moment of 100 kilonewton times 68.7 millimeters. And this makes the additional 6.87 kilonewton meters. So in this case, it can also be, or it can already be very important to consider the influence of the second order theory, because otherwise, your results will be around 7% better, and you will be on the unsafe side of designing your structure. The effect of the second order theory is not linear, by the way. So we can test this by increasing our loads. So let's increase the loads by doubling it. So now we have 20 and 200 kilonewton. Maybe I did not confirm it right now. 20 and 200. Okay. Okay. So now we have again the second order theory at the right side and load case 1 first order theory at the left side. And now we can calculate it again. And yeah, let's see how big the influence of second order theory is right now. So normally after first order theory, we would have a bending moment of 200 kilonewton meters. And with second order influence, we have a bending moment of 230 kilonewton meters. So now the increase of the bending moment is already 15%. It doubled up. So it's definitely not linear proportional. It's non-linear increasing. And I want to show one more thing for this example. And therefore, we want to increase the loads again by factor 5. Okay. And we have to choose the load case 2 again in the right side. And also for the left side, we want to increase the loading by factor 5. Okay, let's check. Load case 1, load case 2, all right. And we can calculate again. And now something special will happen, because now we are getting an error message which says the stiffness matrix is singular, the structure is unstable. And this is for load case number 2, so for second order theory. So in this case, we don't get results because the stiffness of our system is not big enough to be able to transfer the loads to the support. And that's something you can only find out with second order theory. Because if you calculate it with the first order theory, you will get results. You can see we have a bending moment of 500 kilonewton meters here. And we also have a deformation, which is 317 millimeters. So in this case, you would calculate it after first order theory, and you probably wouldn't notice that your system is unstable in reality. and this can be an issue. So yeah, it's important to think about that, and yeah, you need some experience to be able to say if the influence of the second order theory is decisive or not. But you can also use a program which will tell you. For more complex systems, you can use an add-on which is called structure stability, and you will find this in the add-ons tab. Structure stability, the second one, and with this add-on you can find out more about the stability of the system, and yeah, how much you can increase the loads before your system will be unstable. And yeah, therefore we want to have a look at the next example. Okay, and here we have the column again with the same geometry. This time we only have the vertical load of 100 kilonewton, and in this example we want to activate the add-on structure stability and calculate the critical load of this beam. We also want to determine the critical length for buckling about the minor and major axis of the cross section. Maybe some of you already know this this special case, which is called the Euler case 1. That's a very important Euler, or a very important case. And if you already learned this in the university, you probably will already know the critical length for this system. But I would like to show that we can also calculate it with Rfem 6. And we also want to have a look at the different mode shapes. Okay. Now I can delete the second window. We only need one window anymore. And we also can delete the second load case. Okay, so now we only need one load case, and we can calculate with geometrically linear first order theory. Let's also adjust the loads to a vertical load of 100 kilonewton. Okay, so now we are set up, and we need to activate the add-on structure stability in the base data dialog. So I do this right now. Okay. And now we want to go back to the load cases and combinations. And here we see that we have an additional option now, which is called Calculate Critical Load Structure Stability Add-on. So if the critical load is calculated or not can be decided for each load case or load combination. So in this case, we only have load case 1, and we want to calculate the critical load for this particular load case. Therefore, we get a preset. Let's have a look into this preset. Here, the stability analysis type eigenvalue method is chosen. You can also use the incremental method with or without eigenvalue analysis, but for this example, we want to stay at the eigenvalue method. We want to consider the 4 lowest eigenvalues, so that's okay, but you can also increase or decrease the amount. And in the tab Eigenvalue method, you can also choose the eigenvalue method. In this case, we use the Lankosh solver. Okay, let's confirm this and start the calculation. So now you will see that the calculation for this load case is done twice. First for the static analysis and second for the stability analysis. That means that we are getting two different kinds of results. And which kind of result you want to show is choosable in this drop-down menu. You can choose between static analysis, which we had a look at before, so you are already familiar with this overview. But now we want to switch over to stability analysis. Okay, and the table does also get the stability analysis. For the results, we can see the 4 different mode shapes, which we want to have a look at. But first of all, I would like to make this or change the visibility a bit by selecting the options for member deformations section colored so we can see it a bit better. So at the moment we are looking at the first mode shape, and here we can see that the first mode shape is buckling about the minor axis of this cross section. So it's buckling about the let's say the global axis, and the stiffness of this cross section is smaller in this axis. So it's the minor axis. Second mode shape would be buckling about the major axis, so about the axis with the bigger stiffness. And the third mode shape, this is already a higher mode shape, which won't be interesting for us right now. So this mode shape will not appear in reality, because before this mode shape appears, already the first or second mode shape will be reached. In the table, we are getting some results, and the first result is the critical load factor. And this value is calculated for each mode shape. So for the first mode shape, the critical load factor is 4.434. So this means that we would have to increase our load of 100 kilonewton by a factor of 4.434. And then we reach the point where the system is becoming unstable. So if you remember the example we had a look at before, there I increased the loads by a factor 5 and the system got unstable with second order theory. And here in this case, with this member type, with this stiffness of the member, with this geometry, and under this load, the critical load factor would be 4.434. So if I only increase it by 4, so we had a load of 400 kilonewton, the system would still be stable. And factor 5 in this case would mean that the first mode shape would appear and our member would become unstable and buckle about the minor axis. Then we also get the magnification factor, and this factor says how big the influence of the second order theory is. So yeah, this value is always bigger than 1.0. So in this case, it's 1.091, and says that yeah, there is a decent impact of the second order theory to the internal forces. There are also some more results we can have a look at. Therefore, we choose results by member in the table, and we can switch to the tab effective lengths and critical loads by member. Here we also get the results sorted by mode shape. So mode shape 1, 2, 3, and 4. First of all, we are getting the critical load, which is simply our load multiplied with the critical load factor. So this would be 443 kilonewton for the first mode shape. So this load is necessary to make our system unstable. And we get the effective length factors and the effective lengths. And these values are calculated by the critical load and the member stiffness. So for the mode shape 1, which is buckling about the minor axis, we have to look at the second column, so at KCRV or at LCRV. So V means the minor axis always, and U means the major axis. And because we have only buckling about the minor axis, we have to look at these columns. So for the first mode shape, we would have an effective length factor of 2.001. And for the ones who already had this topic at the university, those ones will know that for this system, the effective length factor is 2. So yeah, that's correct, and it makes sense. The effective length would be 20 meters, which is the original member length of 10 meters multiplied with the effective length factor. Okay, for the second mode shape, the results are relatively similar. So we also have our effective length factor of 2.006, which is round about 2. But this time we have to look at the U axis, which is the major axis, because we have the mode shape for buckling about major axis. So you always have to look at the graphic and decide which buckling case it is. Yeah, and for the second mode shape, we would already have a critical load factor of 12.9 or yeah, like round about 13. So to reach this mode shape, it would be necessary to increase the load by a factor 13. So we had a load of 1,300 kilonewton. Okay, so in this example, it was relatively easy and trivial to calculate the correct effective length. But there are also systems where you cannot say it that easy, and therefore we want to have a look at another example. Okay. So, and in this last example, we again want to calculate the mode shapes for this fixed frame, and especially for the columns. And here it is not completely trivial to decide which effective length factors these columns have, because they are held by this horizontal member. And yeah, the stiffness of this member does have an effect, and it's statically over-defined, this system. So it's not completely easy to say this before calculation. And yeah, we want to calculate it with Rfem 6, and we will see that it can be done really easy with the program. Okay, so we want to compare the different mode shapes, and we also want to think about how it would be possible to prevent the frame from buckling out of plane. So this would be this mode shape. Okay, let me quickly modify the system. So this time we have a column length of 6 meters. The columns have an HEB 300. I think that's already correct. Yes. And the horizontal beam is an IPE 300. Yeah, we will have to define this. It's a beam member type, and we need a new section. So let's type this in, IPE 300. With a length of 10 meters. And now we can copy the load, the member, and the fixed support by selecting it and drag and drop with the control button on the keyboard. Okay, I think that should be everything. Let's add the linear dimensioning. 10 meters, okay. And now we can calculate this system again. And first of all, we want to have a look at the mode shapes. Okay, let's switch to stability analysis, which is the interesting part for us now. And the first mode shape is a symmetrical buckling about the minor axis of the column. So in this case, the horizontal member does not have any effect. So it does not hold the columns. It simply moves to the horizontal and y direction. So it does simply nothing. And I think we should also see this if we have a look at the effective length. And for the first mode shape, the effective length factor of our column is still at round about 2 for both members. So here we have the left column, it's 2, and for the right column, if we scroll down a little bit, we also get the effective length factor of 2 for buckling about the minor axis. The critical load factor is also at 12.3. Okay, the second mode shape would also be buckling about the minor axis of the columns. But now that's kind of interesting. We have an asymmetrical mode shape. So yeah, one column goes in negative y direction and the other one goes in positive y direction. The third mode shape, this is also interesting. That's the first mode shape with buckling inside the frame plane. So yeah, now we get buckling about the major axis of the columns. And yeah, this mode shape we want to have a closer look at. The critical load factor is much bigger here. It's 62.1. So the loads, so these nodal loads of 100 kilonewton would have to be increased by factor 62 before this mode shape will appear. Okay, let's see how big the effective length factors for the mode shape number 3 are. So therefore, we have to consider the factor for buckling about the major axis for the third mode shape. So we are in this part of the table, and we have to look at this value. So we have an effective length factor of 1.527, and yeah, this is already not trivial, so it would be kind of hard to calculate this factor by hand. Okay, and for this example, we got another task, which would be to think about how it would be possible to prevent buckling out of plane. So for this mode shape. And yeah, a possible solution would be to add horizontal supports at the top of the columns. And I think we can try this. So we create a new support with translational support in global y direction. Every other degree of freedom is not supported. It's not necessary. And then we can add the supports here. Of course, yeah, if you have such a project and want to calculate the structure, you can only add such a support if it also really is supported at this point. But if you think about this frame structure being just a part of a bigger steel construction, then it could possibly be that yeah, this single frame is supported in global y direction at the upper parts of the columns. Okay, let's calculate one last time. Switch to stability analysis, and now we can see that our first mode shape is already buckling in frame plane. So that was that was the third mode shape before, and now it is the first one. But the critical load factor is still the same. It's 62.1. That means that we eliminated the first two mode shapes. So these two mode shapes won't appear with this nodal support. And yeah, that means that we significantly increased the stability of this whole system, because before we had a smallest critical load factor of I think it was around 12 or so, and now the smallest critical load factor is 62. So now we can increase our loads by a factor 62 before this whole system is becoming unstable. Okay, that's it for this example. And I want to make one last note relating the add-on structure stability. And that is if you only activate the add-on structure stability, you can only take buckling modes into account. So it's important to know this. And if you also want to consider torsional buckling or flexural torsional buckling, it would be necessary to also activate the add-on torsional warping. So yeah, with this add-on activated, or with these two add-ons activated, you can consider all buckling modes, as well as torsional and flexural torsional buckling. But without the torsional warping add-on, you can only consider the normal buckling modes. Okay, now we finished the last example. And yeah, I would like to use the last 2 minutes to do a little advertising for our company. And I would like to point out our career page. There you will find currently open positions, for example, for product development and customer support, which should be the interest to you first and foremost. I assume at least that the majority of the audience are students with technical degree programs. But you can also find other areas such as software development, marketing, or human resources on the Dlubal career page. Yeah, and we also offer internships and working student position. So if you are interested, please stop by, and yeah, we look forward to seeing you. I would also like to advertise the Dlubal website in general as a knowledge portal. And on the one hand, you will find a large number of webinars here and a wide variety of topics relating to the Dlubal programs. You can also watch these webinars afterwards at any time, free of charge. And you can also find the videos on our YouTube channel. We also have an extensive collection of FAQs, knowledge base articles, verification examples, static models for downloading, and much more. Often these articles cover basic theoretical topics in addition to program-specific content. So if you have a question about statics or dynamics during your studies, for example, take a look at the Dlubal website. There is often already an article here that can answer your question. Otherwise, of course, the chatbot Mia is also available to you, or you can contact our customer support if you have a program-specific question. This is free for students. The email address for this is support@dlubal.com.
you can also find the contact form on the website. Okay, now I don't want to keep you from your well-earned evening any longer. If you enjoyed this training, then you are very welcome to visit the other parts of this training series for students, which, for example, go into more detail about steel, wood, or also concrete design, or the finite element method. Okay, with that in mind, I wish you all the best and goodbye.